Hi there. In this video, we're going to be looking at the area inside a closed curve. Let's start off by looking at a closed curve in the xy plane. We draw our xy axis. We have a point A, and that point A has a value of x1, and it's being connected to a point B with x value x2. A is linked to B by one curve. Maybe this curve could be g of x, and B is linked to A also via another curve, maybe f of x. So we could think of maybe a particle that's traveling from A to B and then going back to A via the other curve. So two paths between 2 points. So our task is to find the area inside this closed curve. So the manner in which we would go about doing it is we would find the area underneath the top curve, which is being showed in green, and then we would subtract it from the area underneath the bottom curve, which is being shown in red. So what we're left with is the area inside the closed curve. So we'll just write that down. So we'll let A1 represent the area underneath the top curve, and that's given by the integral from x1 to x2 of f of x dx. And we just want to reverse the order of the integration between the points. So instead of going from x1 to x2, we'll go from x2 to x1. And then we know from our laws of integration, if we do that, if we reverse the path of integration, we need to put a minus sign in front. Why we're doing this will become clear just now. So now we're integrating from x2 to x1, and we have reversed the sign. Now A2 is the area underneath the bottom curve. So that is also from x1 to x2, and that's of g of x. So the area underneath the closed curve, the area inside, that's equal to A1 minus A2, as we have just seen. And then if we write this in terms of the integration, what it would be is the integral of x1 to x2 f of x dx minus the integral from x1 to x2 of g of x dx. So what we're going to do now is we're going to reverse the order of integration as we've indicated here for f of x, and we're just going to put this second term with respect to g of x in front. So we're going to say minus the integral of x1 to x2 g of x dx minus the integral from x2 to x1 of f of x dx. So why have we done this? Well, we have made it look this way because we can now represent this as the path taken by some particle that we were talking about earlier. So imagine that the particle goes from from A to B in the bottom curve. So it goes like that, right? So that would correspond to x1 to x2 of g of x, the bottom curve. Then it goes from B to A by the top curve, and that corresponds to x2 back to x1 of f of x dx. So x1 to x2, then from x2 back to x1. So that's what we're showing. x1 to x2, and then from x2 back to x1. We're just going to take the negative out as a common factor. So what we're left with is the integral from x1 to x2 g of x dx plus the integral from x2 to x1 of f of x dx. So there's just a symbol that's given to represent this kind of integration. That symbol is the integration sign, so we just put the minus there, is a circle. So we would have this minus sign that's in front, and we would have the integral sign, and we would put a circle inside it like that to integrate, to show that it's the integration inside a closed curve. And y corresponds to our two functions, and dx is our variable that we're integrating with respect to. So I think this procedure will be most easily highlighted through a simple example. So we want to find the area between the two curves. Y is equal to x cubed and y is equal to 4x. And the question is, find the area of integration, or find the area inside the closed curve bounded by these two functions. So if we were to just do a quick plot of these two curves, we won't draw the, y is equal to x cubed, the complete thing, but there is a portion of the curve that looks like that, and y is equal to 4x is obviously a straight line. So these two will intersect, and we need to find this point of intersection. And what we're saying is that we want to integrate from this point of origin to maybe this point A, and then back to this point of origin. And maybe as part of the question, we should just say that x is greater than or equal to 0. So that's why we're just considering the first quadrant. So the first step that we need to do is we would determine the intercepts. So when we do that, we basically, we just need to set x cubed equal to 4x, and then we easily see that x is equal to 2. And of course 0. So the intercepts is basically 2 and 0. And then now we need to specify the integration path. So this would be the integration path. And we see that we go from x is equal to 0 to x is equal to 2, and then back to x is equal to 0. So now we've done this, and the third step is to find the area underneath the curve. And that area is given by minus the area inside the bounded curve of y dx. So this is equal to minus, firstly, the integral of the bottom curve from 0 to 2. The bottom curve corresponds to y cubed. Sorry, x cubed. Then back from a to 0. So we're going from 2 to 0, and that corresponds to the function 4x. So if we integrate this, the integral of x cubed is x to the power 4. And we have to put a 1 over 4 in front of it to cancel out the 4. And we're integrating this between 0 and 2. And 4x, if we integrate that, we get x squared. Then 2 times something must give us 4, and that's 2. And that we're integrating that from 2 to 0. So this is something that's not difficult to compute. 2 to the power 4 is 16. 16 divided by 4 is 4. Sorry, don't forget to put the minus in front. So we have minus 4. And then we have 2 squared. 2 squared again is 4. And remember, it's minus now. So it's we put in 0. So this term, the first term is 0. So the second term is minus. So it's going to be minus 2 squared is 4. 4 times 2 is 8. So 4 minus 8 is minus 4. Minus 4 times minus 1 in front is just 4. So this illustrates the procedure of how to integrate inside a closed curve. And in a nutshell, all that we're doing is we're applying the integration along a certain path. We go along the bottom curve, then we go along the top curve, and we integrate just between these two paths. And the method or the formula requires consideration of both these curves, identifying the integration path as I've indicated, and then substituting all of this into our equation. That enables us to find the area inside a closed curve.